Good morning, I am Aditi studying in BSc Chemistry Honours second year. Today in this video we are reading chapter 8 Nitro Compounds. Introduction. Nitro compounds constitute an important class of organic compounds. These may be considered to have been derived from the corresponding hydrocarbons by the replacement of one or more hydrogen atoms by the nitro NO2 group. They are further classified as aliphatic or aromatic nitro compounds according as the nitro group is attached to alkyl or an aryl group. Thus, aliphatic nitro compound alkyl group, aromatic nitro compound aryl group. Nitroalkanes are further classified as primary, secondary and tertiary according as the nitro group is attached to a primary, secondary or a tertiary carbon atom. Thus, primary nitroalkane, secondary nitroalkane, tertiary nitroalkane. Since nitro group is isomeric with the nitrite group, nitro compounds are isomeric with alkyl or aryl nitrites. The chemical properties of these two isomeric classes of organic compounds are quite different, but the nitro compounds are much more stable and find number of applications both in the laboratory as well as in the industry. Therefore, in this unit, we shall briefly study the chemistry of nitro compounds only. Structure of nitro group. According to valence bond theory, the structure of nitroalkenes may be written as, you can say this. The polar structure of nitroalkenes is supported by their large dipole moments. Thus, nitroalkenes may be represented as a resonance hybrid of the following two canonical structure, first and second. You can look at both these structures. The resonance hybrid structure suggests that the two NO bonds are equal. The spectroscopic and diffraction studies have shown that bond length of NO bond is 1 to 1 picometer in nitromethane, which lies in between NO single bond length of 136 picometer and N double bond O length of 114 picometer. Nomenclature. Nitro compounds are solely named by the IUPAC system. The name of any nitro compound is derived by adding the prefix nitro to the name of the corresponding alkane or the arene. Accordingly, aliphatic nitro compounds are called nitroalkenes, while aromatic nitro compounds are called nitroarenes. The positions of the nitro group and other substituents, if any, on the parent nitroalkane or the nitroarene are indicated by Arabic numbers 1 to 3, etc., with a carbon atom bearing the nitro group getting the lowest possible number for aromatic nitro compounds prefix. For 1, 2, M for ortho for 1, 2, meta for 1, 3 and para for 1, 4 are also used. Some typical examples are given below: nitromethane, nitroethane, 1 nitropropane, 2 nitropropane, 2 methyl 1 nitropropane, 2 methyl 2 nitropropane, 2 nitroethanol, 2 methyl 1 4 dinitrobutane, 3 bromo, 3 5 dimethyl 5 nitropentane, heptane, nitrobenzene, 2 nitrotoluene, 4 nitrotoluene, 1 3 dinitrobenzene. Preparation of nitro compounds. Preparation of nitroalkanes. Nitroalkanes are usually prepared by the following methods from alkanes. Alkanes undergo nitration only with forming HNO3 in the vapor phase at 673 Kelvin to form nitroalkanes. This method is called vapor phase nitration. Methane plus forming nitromethane. Limitation. Nitration of higher alkanes not only gives a mixture, other nitroalkanes containing lesser number of carbon atoms resulting. Bonds are also formed. Beside these oxidation products like CO to NO2, say ethane to nitroethane, propane to 1 nitropropane to nitroethane plus other oxidation. The reaction occurs by a free radical mechanism and the case of such order tertiary, secondary, primary. Merits. Due to the formation of complex mixture of products, this preparation of nitroalkanes, however, this method is widely for the since they are used as industrial solvents only. From alkyl halides. Alkyl bromides and iodides, especially silver nitrate in alcohol to give excellent yield, 70 to 80% of nitroalkanes, 15% of alkyl nitrites. Alkyl halide, silver nitrite, nitroalkane, 1-bromobutane. Explanation. This reaction is an example of a nucleophilic substitution reaction. Nitrite ion, like cyanide ion, is an ambident nucleophilic and hydrogen through which it can attack an alkyl halide, whereas attack these nitro compounds attack through oxygen gives nitriles. Alkali metal nitrides are ionic compounds and hence have a negative charge on one of the oxygen atoms. Nucleophilic attack through this negatively charged oxygen atom on the alkyl halides mainly gives alkyl nitrides. In contrast, silver nitride is a covalent compound and hence does not have a negative charge on oxygen atom. Instead, both oxygen and nitrogen atoms carry lone pairs of electrons. Since nitrogen is less electronegative than oxygen, therefore lone pair of electrons on nitrogen are more easily available for bond formation. In other words, nucleophilic attack occurs through nitrogen and hence silver nitride predominantly gives nitro compounds. Demerits: aromatic nitro compounds cannot be prepared by this method. This method is not suitable for the large scale preparation of nitro compounds from tertiary alkyl amines. Primary amines containing a tertiary alkyl group on oxidation with KMnO4 gives excellent yields of the corresponding nitroalkenes. Preparation of nitroarenes. Nitroalkanes are invariably prepared by direct nitration of arenes with a mixture of concentrated HNO3 or fuming HNO3 and concentrated H2SO4, for example, benzene plus concentrated HNO3 to nitrobenzene. The mixture of concentrated HNO3 plus concentrated H2SO4 used for nitration of aromatic compounds is called the nitrating mixture or the nitrating agent. Other nitrating agents which have been used for nitration of aromatic compounds are nitric acid, acetic anhydride mixture, HNO3 plus CH3CO2O, acetyl nitrite, nitronium perchlorate, nitronium tetrafluoroborate, etc. Mechanism: nitration is a typical example of an aromatic electrophilic substitution reaction in which the nitronium ion acts as the electrophile. The function of H2SO4 is not that of a dehydrating agent but acts on HNO3 to form the reactive nitronium ion as shown below. Nitric acid to nitronium ion. This electrophilic substitution reaction occurs by the following two-step mechanism. Benzene and other arenes are electron-rich molecules. In the first step, the electron-rich benzene molecule nucleophile attacks nitronium ion electrophile, leading to the formation of carbocation, which is stabilized by resonance. During this step, the aromatic character resonance energy of 150 kJ mole is sacrificed. As a result, this step is slow and hence is the rate determining step of the reaction. Second step. In the second step, the carbocation formed in step 1 loses a proton to yield nitrobenzene. Since during this step the aromatic character of the benzene ring is restored, therefore this step is fast and hence does not affect the rate of the reaction. Evidence in support of the mechanism. This mechanism is supported by the isotope effect. It has been found that when hexadeutropbenzene is nitrated, the rate of nitration is exactly the same as that of benzene. Since A-C-D bond breaks more slowly than CH bond, therefore the loss of a proton is not the rate determining step. Had it been so, the rates of nitration of benzene and hexadeutropnitrobenzene would have been different. Choice of the nitrating agent. The choice of the nitrating agent to be used for nitration of a given compounds depending upon the following two factors: nature of compound to be nitrated, number of nitro groups to be introduced, the presence of electron donating substituents like CH3O, CH3OH, NH2, etc. activate the benzene ring by stabilizing the intermediate carbocation. Therefore, nitration of these compounds is carried out under mild conditions. For example, nitration occurs with dilute HNO3 even at room temperature. In contrast, presence of electron withdrawing groups such as NO2, COOH, CN, SO3H halogens deactivate the ring by destabilizing the carbocation. Therefore, for nitrating such compounds or when it is required to introduce more than one nitro group, the nitration is carried out not only by using a strong nitrating mixture but a higher temperature is also required. For example, nitration of nitrobenzene, which contains the electron withdrawing NO2 group, is carried out with a mixture of concentrated HNO3 plus concentrated H2SO4 at 393 Kelvin. Nitrobenzene to metadinitrobenzene. Physical properties of nitro compounds. Physical state: color, odor, etc. Nitroalkenes are colorless when pure, pleasant smelling like liquids. Aromatic nitro compounds can be either pale yellow liquids or solids with distinct smell. For an example, nitrobenzene is a pale yellow liquid having the smell of bitter elements and is known as oil of myrbane. Boiling points. Both nitroalkanes and nitroarenes are highly polar compounds, dipole moment between 3,4D, and thus have strong dipole-dipole interactions. As a result, they have much higher boiling points than hydrocarbons of comparable molecular masses. For example, you can see some compounds with molar mass, boiling point, and dipole moment. Further, nitroalkenes also have much higher boiling points than the less polar isomeric alkyl nitrites. For example, the boiling point of ethyl nitrite is 261 Kelvin, while the isomeric nitroethane has a boiling point of 388 Kelvin density. All the nitroalkanes and nitroarenes are heavier than water. Solubility: nitroalkanes are sparingly soluble in water while nitroarenes are insoluble. However, both nitroalkanes and nitroarenes are readily soluble in organic compounds. Solvents: stability: when heated strongly, polynitro compounds decompose with explosive violence. Tautomerism: like aldehydes and ketones, nitroalkanes containing alpha hydrogen atoms, primary and secondary nitroalkanes show tautomerism. For example, nitromethane exists in two tautomeric forms. You can look these both tautomeric forms. The nitro form first is often called the pseudo-acid form, while the isonitro form second is called the acinitroform or nitronic acid. The equilibrium, however, almost completely lies towards left due to resonance within the nitro group. Stabilization of nitroform first. Similarly, nitroethane, 1 nitropropane, 2 nitropropane show tautomerism, while aromatic nitro compounds, that is nitrobenzene, metadinitrobenzene, etc., which do not contain alpha hydrogen atoms, do not show tautomerism. Acidic character: the alpha hydrogen atoms of primary and secondary nitroalkanes are weakly acidic and thus can be abstracted by strong alkalis such as aqueous NaOH. Therefore, primary and secondary nitroalkanes dissolve in aqueous NaOH to form salts. For example, nitroalkane. The main reasons for the acidic nature of primary and secondary nitroalkanes are the strong electron withdrawing inductive effect of the nitro group and the resonance stabilization of the carbanion formed after removal of a proton. Although primary and secondary nitroalkanes are weakly acidic, yet as compared to aldehydes and ketones, they are twice as strong. For example, of nitromethane is 10.2 while that of acetone is 20. Nevertheless, nitroalkanes are neutral to litmus. Acidification of the sodium salt with a weak acid gives the nitro analog of an enol called the acinitrotautomer. Unlike the anols of aldehydes and ketones, which are readily converted into the keto form, the conversion of acinitro form into the nitro form is a relatively slow process. Consequently, acinitro form can be generated as metastable intermediate in high concentration by careful acidification of the salts. The acetonitro derivatives are relatively stronger acids, as is evident from their pKa values. Reactions of acinitro form with electrophiles and nucleophiles. One of the remarkable features acinitro forms is that they can behave as nucleophiles as well as electrophiles and thus react with electrophilic and nucleophilic reagents. Reactions in which acinitro derivatives act as nucleophiles. Some reactions of this type are discussed below. Aldol condensation. The carbanions of nitroalkanes being nucleophilic react with electrophiles and as aldehydes and ketones to form aldol type addition products which spontaneously undergo dehydration to give alpha beta saturated nitro compounds, unsaturated nitro compounds. For example, here's the example of nitromethane acetaldehyde. You can look at both these examples. The driving force for this dehydration is the gain in stability due to the conjugation of ethylenic double bond with the double bond of the nitro. Second is Michael addition. Like aldehydes and ketones, alpha beta unsaturated carbonyl compound act as electrophiles and thus react with nucleophilic acinitroform to form Michael type addition products. For example, nitroalkane, acetonitroform addition product. Third is halogenation. Acinitroforms generated from primary and secondary nitroalkanes in presence of alkali, being nucleophilic, react with electrophiles such as halogen, chlorine or bromine. In presence of alkali to form halonitroalkanes, During this reaction, all the alpha hydrogen atoms of nitroalkenes are successively replaced by the halogen atoms. For example, nitromethane to trichloronitromethane, nitroethane to nitropropane. Tertiary nitroalkyls do not undergo halogenation because they do not have alpha hydrogen atoms. Chloropicrin obtained above is used as insecticide as well as constituent of tear gas. Reactions in which Ac-nitrofoam act as electrophiles. An important reaction of this type is Neff-carbonyl synthase. Neff-carbonyl synthase, when the solution of sodium salt of nitronic acids is acidified with H2SO4 at room temperature. Primary nitroalkanes give aldehydes while secondary nitroalkanes give ketones. During these reactions, the S-nitroform acts as the electrophile and water as the nucleophile. For example, sodium salt of nitronic acid. You can look at this. Similarly, sodium salts of nitronic acids derived from secondary nitroalkanes on treatment with 50% H2SO4 gives ketones. Sodium salt of nitronic acid to ketone. This reaction is called Neff-carbonyl synthase. The main advantage of Neff-carbonyl synthase is that the reaction is often violent and gives unsatisfactory yields. Hydrolysis. Primary nitroalkanes, when treated with boiling HCl or 85% H2SO4, undergo hydrolysis to form a carboxylic acid and the corresponding salt of the hydroxyl amine. Nitroalkane to carboxylic acid plus hydroxylamine hydrochloride. Nitromethane to acetic acid hydroxylamine hydrogen sulfate. This reaction is used for the manufacture of hydroxylamine. In contrast, secondary nitroalkanes upon hydrolysis with boiling HCl give a ketone and nitrous oxide. Secondary nitroalkane to ketone and nitrous oxide. 2-nitropropane to acetone and nitrous oxide. Tertiary nitroalkanes, however, do not generally undergo hydrolysis with hydrochloric acid. Action with nitrous acid. Primary, secondary, and tertiary nitroalkanes behave differently towards nitrous acid. Primary nitroalkanes react with nitrous acid to form nitrolic acids, which dissolves in alkalis to form a red solution. Primary nitroalkane to nitrolic acid. Secondary nitroalkanes react with nitrous acid to form blue-colored pseudonitrols, which do not dissolve in alkali. Secondary nitroalkane to pseudonitrile. Blue coloration does not dissolve in alkali. Tertiary nitroalkanes do not react with nitrous acid since they do not have alpha hydrogen atoms. Manish reaction. Primary and secondary nitroalkanes also undergo Manish reaction. For example, primary nitroalkane to dimethylamine, secondary nitroalkane to diethylamine. This reaction can be used for the preparation of nitroamines and diamines, etc. Reduction. One of the most important reactions of nitro compounds in their reduction, depending upon the nature of the reducing agent and pH of reaction medium. Nitroalkanes give different products as shown below. Reduction in acidic medium. Nitroalkanes can be reduced to the corresponding primary amines by a combination of some active metal like zinc, iron, or tin and concentrated hydrochloric acid, for example, nitroethane to ethylamine hydrochloride, ethylamine salts. Reduction in neutral medium. In the neutral medium, zinc dust, nitroalkanes are reduced to the corresponding hydroxylamines, for example, nitromethane to N-methyl hydroxylamine. Catalytic reduction or reduction with LiALiH4 nitroalkanes can be corresponding primary amines with either LiAIH4 with H2 in presence of a nickel, platinum, palladium, carbon in ethanol. For example, look at this example, nitroethane to ethylamine. Chemical reactions of nitroarenes. Some important reactions of nitroarenes are discussed below. Acidic nature. Unlike primary and secondary nitroalkanes, nitroarenes do not have any, like tertiary nitroalkanes, they do not exhibit acidic character or tautomerism. However, one, two, or more nitro group attached to the benzene ring are somewhat acidic, thus often react with cold aqueous alkali to form strongly colored salts. Reduction. One of the most important reactions of nitro compounds is the amine. The reduction is believed to occur through the following stages. Nitro compound to nitroso compound, a substituted hydroxyl amine. The final product, however, depends upon the pH of the reaction medium and agent. Reduction in the acidic medium, like aliphatic nitro compounds, aromatic, be reduced to the corresponding amines by a combination of some active metal concentrated hydrochloric acid, for example, nitrobenzene, to aniline hydrochloride. Under acidic conditions, the intermediate products nitroso compounds reduce even more readily than the parent nitro compound and have hence only the primary, the final product. Mechanism. The mechanism of reduction of nitro compounds to amines involves a number of steps in which addition of electrons and protons from the acid takes place, and nitrosobenzene and phenyl hydroxylamine are the intermediates. Catalytic reduction. Like aliphatic nitro compounds, aromatic nitro compounds can be reduced to the corresponding primary amines with hydrogen in presence of a catalyst such as iron and nickel, platinum or palladium carbon in ethanol, for example. Look at the example. Reduction in the neutral medium. In the neutral medium, zinc, dust and NH4Cl solution, aromatic nitro compounds like aliphatic nitro compounds are reduced to the corresponding hydroxylamine, for example, nitrobenzene, to N-phenyl hydroxylamine. These hydroxylamines, when warmed with Tollens reagent, are easily oxidized back to the corresponding nitroso compounds and thus reduce Tollens reagent to the metallic silver. This reaction is used as a test for nitroso compounds under the same Baker-Milkins test. Reduction in the alkaline medium. The reduction of the aromatic nitroso compounds in the alkaline medium gives different biomolecular reduction products depending upon the nature of the reducing agent employed. For example, nitrobenzene to hexoxybenzene, azobenzene or hydrozobenzene. These biomolecular reduction products are actually formed by condensation of primary products of reduction, nitrosobenzene and phenyl hydroxylamine. Azoxybenzene is formed by the base-induced condensation of nitrosobenzene and phenyl hydroxylamine. And phenyl hydroxylamine nitrosobenzene to azoxybenzene. Similarly, it can be shown that further reduction of azoxybenzene first gives azobenzene and then azobenzene. Reduction with LiAH4, reduction of nitrosobenzene with LiAH4 also yields azobenzenes. It may be noted here that reduction of aliphatic nitro compounds with LiAH4, however, gives the corresponding primary amines. Electrolytic reduction. Electrolytic reduction of nitrobenzene in weakly acidic medium gives aniline, but in strongly acidic medium it gives para-aminophenol, obviously through the acid catalyst rearrangement of the initially formed phenyl hydroxylamine. Nitrobenzene to aniline, nitrobenzene and phenyl hydroxylamine to para-aminophenol. Selective reduction. If two or more nitro groups are present in the benzene ring, it is possible to reduce one of them without affecting the others. Such reductions are called selective reductions. For example, reduction of meta-dinitrobenzene with sodium or ammonium sulfide gives meta-nitroaniline. Meta-dinitrobenzene to meta-nitroaniline. This reduction of nitro compounds with sulfides and polysulfides is called Zinin reduction. Electrophilic substitution reaction. Nitro compounds, like other aromatic compounds, undergo electrophilic substitution reactions such as halogenation, nitration and sulfonation. Since NO2 group is a powerful electron withdrawing group, it is strongly deactivating and meta-directing. This may be explained as follows. Nitrobenzene can be represented as a resonance hybrid of the following structures. Look at these structures. It is evident that nitro group, because of its electron withdrawing nature, reduces electron density more at ortho and para positions than at meta positions. In other words, electron density is comparatively more at meta position than ortho and para positions. Therefore, nitro groups is meta-directing further since the NO2 group is strongly deactivating. Therefore, these reactions occurs only under basic drastic conditions. For example, meta-bromo-nitrobenzene, nitrobenzene, meta-dinitrobenzene. It may be noted here that because of strong electron withdrawing nature of the nitro groups, the electron density of the benzene ring decreases to such an extent that meta-dinitrobenzene does not undergo further renitration to give symmetrical trinitrobenzene. Therefore, it is prepared by indirect route. Nitrobenzene does not undergo Friedel-Crafts reaction. Friedel-Crafts reaction, nitrobenzene is used as a solvent. The presence of nucleophilic substitution reactions, the presence of resonance structure second to fourth suggests that nitrobenzene can also understand at these positions. These reactions, however, occur with strong nucleus. Example, nitrobenzene when fused with solid KOH gives a low yield. Thus, nitrobenzene to orthonitrophenol mechanism. The mechanism of this reaction is an example of reaction. In the first step, the nucleophile adds to the benzene ring stabilized by resonance, also involving the nitro group. In the second ion, which is a very strong base and hence a poker leaving group, out either at high temperature or in presence on an oxidizing agent. Complete mechanism is outlined below by considering the formation. Look at these complete mechanism. Replacement of nitro group. We have seen above that nitro group of nitrobenzene remains intact on treatment with alkali. However, this nitro group can be displaced as nitrite ion by nucleophiles if another nitro product is present at ortho or para positions. For example, O-dinitrobenzene, orthonitrophenol, orthonitrophenol, and orthonitroaniline. This is picric acid 2,4,6 trinitrophenol. Direct nitration of phenol with a mixture of concentrated HNO3 plus concentrated H2SO4 gives only a low yield of picric acid because nitric and being a strong oxidizing agent oxidize phenol to terry products. It is therefore prepared commercially by the following methods from phenol. Phenol is first sulfonated to give phenol 2,4-disulfonic acid, which is then nitrated. During nitration, the two sulfonic acid groups are replaced by nitro groups and a third nitro group is introduced at the ortho position. Phenol to phenol 2,4-disulfonic acid to picric acid. From chlorobenzene, picric acid is obtained from chlorobenzene by the following sequence of these reactions. Physical properties. It is a yellow crystalline solid with melting point 395 Kelvin, sparingly soluble in water, and it is soluble in alcohol and ether. It has a bitter taste and hence the name. Chemical properties. Some important chemical properties of picric acid are described below. Acidic nature. Due to the presence of the three nitro groups, picric acid is a very strong and hence decomposes carbonates and bicarbonates involving CO2 gas. Reaction with PCl5. When treated with PCl5, it forms picryl chloride. The Cl atom chloride is very reactive and thus gets hydrolyzed to phenol on just boiling with water. Concentrated ammonia picryl chloride gives picramide. Reduction. On selective reduction with Na2S, picric acid gives picramic acid. Formation of picrates. It forms charge transfer complexes known as picrates with electron-rich compounds such as aromatic hydrocarbons, amines and phenols. Picric acid plus mesitylene. Picrates are yellow, orange or red colored solids with definite melting prints and hence are often used as derivatives to characterize above classes of compounds. Uses. Picric acid is used as explosive as a direct yellow dye for wool and silk and in medicine. as an antiseptic for burns. It is also used as a laboratory reagent for characterization and purification of polynuclear aromatic hydrocarbons, amines, and phenols. Halonitroarenes. Arenes containing both halogen and nitro groups are called halonitroarenes. For example, there are three isomeric halonitroarenes having one halogen atom and one nitro group attached to the benzene ring. Orthohalonitrobenzene, metahalonitrobenzene, parahalonitrobenzene. Chemical reactivity of halonitroarenes. Haloarenes are unreactive towards nucleophilic substitution reactions, but the presence of nitro groups at ortho and para positions with respect to the halogen atom facilitates nucleophilic substitution reactions of halonitroarenes by stabilizing the intermediate carbanion as shown below. You can look at these steps. Evidently, more the number of nitro groups at ortho and para positions with respect to halonitroarene. Look at this. It may, however, be noted that the presence of nitro groups at meta position activate the halogen to the same extent as that ortho and para positions, since the weak I effect and maybe the strong R effect of the nitric group. Thank you.